All right, so we talked about two different ways so far to determine the enthalpy change for a reaction, or this delta H reaction. We said we could do it experimentally. That's where we started the chapter. So that was using this idea of calorimetry. If we know the specific heat of the substance in that calorimeter, and in the example we did was water, and we measure the temperature change, and we know the mass of the substance, then we can equate that back to a heat or an enthalpy change of whatever the reaction was. We did an example like that with silver chloride. That was experimentally. Not all things can be done experimentally or aren't cost effective to do it that way. So we have two other sort of computational ways to tabulate these things. The first of which in the sort of computational regime was Hess's law. And that's really just taking an overall reaction. We did this for the water gas or the gas shift reaction, and if you add those up in a way that you can rearrange those individual component reactions such that they yield the overall reaction, because enthalpy is a state function, we can do that. We can rearrange them in any way we want, adjust the enthalpy, and then add them all up. We just did an example of that. The third way that we're going to talk about here in this video is the process of standard heats of formation. All three of these should give you the same answer, ideally, right? Experimentally and computationally, those things sometimes can give you different answers, but these two will definitely give you the same answer every time, because they're both computational methods, and they're just taking other values and adding things up. So these two are equivalent to each other, but they're different ways to get to the same answer, which is the overall change in enthalpy for the reaction. So the heat of formation of a substance is actually pretty straightforward. We denote that as delta H sub F. So this is the heat of formation. And it's the enthalpy change for the formation of 1 mole of a substance in the standard state. But the key here is underlined in blue, from its elements. And so it's a hypothetical reaction. It doesn't have to be experimentally true, but we could write out a balanced chemical reaction for a molecule from its elements, from the basic elements on the periodic table, and we could assign a particular energy for that. That's what the heat of formation is. I'll tell you in a second, once we sort of figure out what that means to us intuitively, how those can be used, if we have a table of these values, how those could be used to compute ultimately the delta H of an overall reaction. So this formation is for one substance, but we can use multiple heats of formation to compute the delta H of reaction. That's what this video is going to show you. So an example of a heat of formation, this delta H sub F, is again the enthalpy change for the formation of 1 mole of a substance in its standard state from its elements. So if we wanted to figure out what the heat of formation for methane gas was, we would write a hypothetical reaction, doesn't have to be real, but a hypothetical one that's balanced from the original elements to comprise that. And so the simplest way to make CH4 would be to combine carbon and hydrogen, the two elemental forms that comprise this, and then write up what is the energy change, meaning energy yielded or energy input, when we make that compound from its elements. And in this case, the heat of formation is minus 74.8 kilojoules per mole. Coincidentally, if we looked at what the actual enthalpy of reaction here, delta H of reaction, for this reaction, for the one written here, it's also minus 74.8, as you'd expect, right? These two things in this circumstance are exactly the same. So if you want to form a molecule from its individual elements, that's the heat of formation, which in this case would also be the heat of this chemical reaction. They're going to be the same. The reason this convention works here in this case is because arbitrarily we just assigned, as chemists and scientists 100 years ago plus, that the delta H of formation of an element is 0. In that case, if we wanted to form carbon or form hydrogen gas, we'd say that that itself was 0. That's not actually true, But it doesn't matter because we're actually just measuring the delta of something. So it doesn't matter what our starting point is. The actual, heat of formation of carbon could be 10 or 100, and this could be 90 or 50 or whatever. It doesn't matter because the delta here would still be the same, and that's the key. So the heat of formation of the substance is going to be how much energy it takes to form it from its elements. And still, we still haven't gotten to the original point, which is how do I use that to get to the heat of reaction for a more complex reaction. I said in this case they're the same, but in many cases they're not the same. So let's do a real example here. Before we do that, I should also state that, in general then, the delta H of a reaction is going to be the delta H formation of the products minus the delta H of formation of the reactants. In other words, sort of just like Hess's law, we can take all of the heats of formation of a reaction and see how much energy it took to form those products, and subtract that how much energy it took to form those reactants from their elements. And because again these are state functions, doesn't matter what the process is to get there, it's still going to give you the overall change in energy of the reaction. So let's do an example. All right, so we'll come back to a reaction we've done several times here. This is the fermentation of glucose. This is sugar glucose. I'll write that below here. Fermentation in yeast to produce ethanol here and carbon monoxide. Okay, so what I'm showing you at the top in this table, this is just a really short table. These tables can be hundreds of pages long. These are these huge tables that show heats of formation for all sorts of substances from their elements. What we can do then is, if we want to compute the delta H of the reaction, what we just stated was that was equal to the sum of all of the delta H's for the products minus the sum of all of the, I should say, delta H of formation of the products minus the sum of all the delta H formations of the reactants. So the other way of saying this is we sum up all the energy that it took to produce the products from their constituent elements, and we subtract all of the heats of formation, or the energy required to form those reactants from their elements. The net difference between those two is going to be the actual change in energy of the bonds forming and breaking in that specific reaction. So what we need to do then is to look at a table like this, add up the sum of the delta H of formation, which is shown in this column, for the products, and subtract that from the reactant. So let's do that below. Okay, so I filled out this expression here. I'll walk you through it. So if I'm trying to compute the overall delta H of reaction, which is what we're being asked, so for this reaction, we want to use the heats of formation of the individual molecules of the reaction to compute the overall energy change in the breaking and forming of these bonds. So that means we need to sum up all the heats of formation for the products and then subtract the heats of formation of the reactants. So I'm starting with our products over here. So products are ethanol and CO2. We've got 2 moles of each. So if I go back down here to my red text, I'm going to start with ethanol. I'm going to find it in the table. So ethanol is right here. So that means that its heat of formation from its raw elements, which would be oxygen, hydrogen, and carbon, you don't need to know the reaction, doesn't matter. You just need to know that its formation energy would be minus 277.7 kilojoules per mole. That's what I have here. And I have 2 moles of them, which means that this unit and this unit go away, and I'm left with 2 times minus 277.7. That's the heat of formation of 2 moles of ethanol in this reaction. I'm going to add that then here to the heat of formation of 2 moles of CO2. So again, 2 moles CO2, I'm going to find carbon dioxide, which is minus 393.5 here. I'm going to punch that in right there. 2 moles, moles go away, so it's 2 times 393. This is the sum of the formation energies for the products in black here, this whole side. I'm going to subtract from that then the sum of the formation energies of all the reactants. In this case, we only have one, which is glucose. We have 1 mole of it, and glucose has 1273.3 kilojoules per mole, which I put here. So mole, mole. That allows me to subtract and sum this up. What I get away out of this with is delta H reaction is equal to minus 69.1 kilojoules. Not kilojoules per mole, remember, this is kilojoules. The moles have gone away. What does that mean if I just have kilojoules? What does the heat of reaction here in thermochemical equations, what does that actually pertain to? Remember, that pertains to the reaction as written, and that's the case here. Okay, so what does this mean? Why did we do all this? Well, this is just an alternative route to the same answer. So we could have, if we had a table like this, and we had a bunch of heats of formation, we could compute what the overall delta H of the reaction is for the system. If we instead had a bunch of different chemical reactions that all added up to this reaction, we could have equivalently done this with Hess's law. I'm going to show you how to get there here in a second as well. All right, so I've got the same example, the fermentation of glucose, but now being tabulated using Hess's law, just to show you that you arrive at the same answer. So this is the table of different chemical reactions. Notice that these reactions are coincidentally all the same as the heat of formation reaction. So this is the heat of formation of glucose, but in reverse, so from its elements here. This is the heat of formation of ethanol from carbon, hydrogen, and oxygen, and the heat of formation of CO2 from carbon and oxygen. And so I multiply both of these by 2 to get this reaction to equate, and add these all up. You get the net reaction, the same as we wanted to start with. Take their individual delta H values, multiply both of these by 2, and you end up getting the same answer. So either way, depending on what data you have accessible to you, if you have these reactions and these values, great, use Hess's law. If you don't, if you have tabulated delta heat of formations, then use the sum of the heat of formations of the products minus the sum of the heat of formation of the reactants to get what the overall delta H reaction is. So those ways are both equivalent.